In the second section, we start with the first method for quantifying spatial variability, which is called variogram, or also semi-variogram. So in this first session, we'll talk about just calculating variogram. Then we'll talk about kriging. I'd like to talk about kriging before modeling variograms, because modeling variogram is a somewhat more theoretical aspect and becomes more clear once we know what the particular purpose is of using variograms. So there are a number of references. There are many, of course, books references. I like these two. The Teacher's Aid by Gringarten and Deutsch. And then also we'll be using the variogram methods implemented in SGEMS, and Chapter 5 also has some introduction on variogram calculation. So the question is sort of as follows. Suppose you're given some kind of data set, which could be an exhaustive data set, such as here. This is a topographic data set of Walker Lake on the Nevada-California border, or you're given some point data. So the question is, how would you quantify variability that you can observe? And so we see some clear, let me put up my pointer, some clear interesting features. We see this high feature here, which seems to be quite extended. Then we see a valley that is quite extended as well, and then seems we have some kind of heterogeneous kind of behavior over here. So the question is, how do we quantify this with mathematical models? So the basic, before doing that, I'd like to already introduce the basic geostatistical model. Because as we've seen in the previous slide, there are some features that are quite unique to the pictures, and some features that have some what I call repeats. There's textures that repeat themselves, and there are textures or elements of the image that don't repeat themselves, such as the mountain valley that occurs just once in that image. So in geostatistics, because it's a statistical science, we treat that first part as unique, but unknown, of course. We may not know where the mountain valley is. But we may have some information about it through data. But we also treat it as non-stochastic. It means we are not going to treat it as an estimation problem, which then has an estimation variance. So the repeats, however, we treat as stochastic, but we treat them as zero mean. So in geostatistics, then, you could say broadly, there are a number of methods that use this kind of idea, where we say that our variable, our spatial variation, x here is here, x, y, z, is some kind of a slowly varying function and a fast varying function, and that fast varying function has zero mean. So that's why also, if you take the expected value of this, then we end up with this. So this could be seen as a mean variation, but not necessarily in a stochastic sense. As I said, we're going to treat this more in a unique fashion. So this model is an additive model, and it works pretty well in many situations, but also many situations where that doesn't really apply. So here, let's say that I have an image. Imagine that I take some smoother of that image to get the smooth image, and then I subtract that image, and I get this image here. So we clearly sort of taken out some unique features of this image, which could be these, notice these high areas. We end up with some nice sort of regularly varying image where we notice that in this part of the image looks very similar to that part of the image, and that we'll call later a notion of stationarity. So that works well here, doesn't work well here. Again, if I take a smoother, remove that sort of mean, I see that I have higher, a lot of high over there, then I end up with this image, and still we need to find unique features, which is, for example, that if I take a look at this side of the picture, compare that with that side of the picture, then I notice a difference in the angle. And so this mean doesn't necessarily remove all these unique features. And that has to simply do with this additive property, that there are elements of images that are non-additive and that are also unique. And that's something we'll treat later when we deal with multiple point geostatistics. So If we then look at this residual image, we'll introduce a number of terms. It's important to use the sort of the right nomenclature here. So variance is simply taking all these values in this picture and calculating the variance of those values. So correlation length will have something to do with the kind of correlation that we notice in this direction. We see a strong correlation. This direction, we see less correlation. And that also has then to do with what we call anisotropy, which is there's clearly a variation in the image that is in one direction different from another direction. Smoothness will have to do something when we observe the image at very small scale. So for example, what we notice here, if I would be in a certain pixel and then move to the left and the right, we see some variation. And so the image is not quite smooth. You'll see later on that there are images that are much smoother than this image. And so we have to quantify that. And then there's just simply random noise. As we will see later, this image doesn't have random noise, but there have to be ways of random noise means basically that if I'm at a certain position, I go left, right, up, down, then I get a signal that cannot be predicted. So this is just random noise. Okay, so how do we proceed in quantifying that? So we'll start first with data that's on a regular grid. So here's my regular grid, and attached to that grid, I have values associated with that particular grid. As we saw, that could be just an image from the previous slide. So the first thing I will do is I'll define a vector, which connects 2 points. So here we have a vector that connects this point and that point. And so if I have this vector here, then I can look at this value here, so say it's 20, and look at this value here, it's 30. And can now start creating a scatter plot where on the y-axis I have what is called the head value, which is this, and the tail value, which is that. So this is the tail value, this is the head value, and I have one dot in that point. So this is the say the value 20 and the value 30. So yeah, sorry here, this is a wrong notation. So this is obviously the head value, this is the tail value. So now what I'm going to do is I'm going to keep the direction the same, and the lag distance the same, but I'm going to scan for more of those pairs. And so that is what is done here. So I create many of these pairs, and that all these values become dots in this scatter plot. And then we notice something. We notice that there's correlation. So that means on average, when I compare two values at that lag distance and that angle, that I have a correlation between those values. And so I can calculate that correlation coefficient, and then I have a measure of degree of correlation, or a quantitative measure of what I observe in that image at that lag distance and angle. So what I'll do in the next slide is to keep the angle constant and then increasing the lag distance. So now instead of going this point to that one, I will go from this point to that point. And then I scan again the entire image and create a scatter plot. And I will continue that operation. So what I'll do is I will calculate correlation coefficients that are, of course, function of lag distance, but are for a constant angle. And then later, of course, I will start varying the angle. So that is what we call a correlogram. So if we do that, and we do that for constant angle, but different lag distance, so here are various lag distance, we calculate this function, which is the experimental correlogram. And of course, I can repeat this now for different angles, and I will get a different correlogram. Okay, so here we have an example experimental correlogram from the previous slide. So a number of properties we should note is that it always has to start at 1. And that has to do, of course, with the fact that if a value correlates perfectly with itself. Then it will start decreasing as we increase distance, which indicates, of course, if things are further apart, they become less and less correlated. And at some point, that correlation will become 0. Here, it's exactly 0. That doesn't have to be like that. It may start to fluctuate around 0. And so there's a distance here of, say, 10, beyond which we see no correlation. That means that, on average, between any two values that are more than 10 units apart, we see no correlation. Okay, so now I can start doing this for various directions. And so here are then various of these correlograms for various directions. And so here's a correlogram in the north direction, in the west direction, and this is in the northeast direction. So because of the nature of this image, we notice that we see much more correlation length. So the size of these black and white bodies, let's say, are much longer in this direction than in that direction. And so that translates then into a correlation length of here 12 that is larger than in any other direction. So for example, north is 4, west is 4, etc. And so that is what we call anisotropy. So anisotropy is basically the variation of the correlation length with direction. Okay, so then anisotropy just means simply the absence of that dependency of the correlation length with direction. And so here, clear in this picture, our black and white areas are sort of at the same size depending on what direction we're looking. And so if you calculate then the correlogram in those various directions, you find approximately that we're looking at 8 to 10 in terms of correlation length. Okay, so we talked about anisotropy. Now we'll talk about this issue of smoothness. So here we have two images, and they're clearly, one is clearly smoother than the other. And so smoother simply means that in this particular case is something that we need to look at short distance. So if I'm here in this black area and look at one particular pixel, and I were to go above, below, left, right, I will see something that is very similar. And even if I go a little further, I still see something that's very similar. It means that once you're in black, on average, you will stay in black at a short distance. And once you're in white, on average, you will stay in white at short distance. And so in terms of the correlogram, what that simply means is that we start here at 1 for the correlogram, and then we'll start to decrease only very gradually. See that the correlation coefficient remains relatively high and then goes down. This is not the case in this image. Now, actually, this image has exact same correlation length as the image, or at least approximately. So the correlation length is the same, and anisotropy is the same. But it's clear that when you move from left to right here, top to bottom, then we'll see bigger changes more rapidly. And so that manifests itself here is that we get a faster decrease. Actually, we get an exponential decrease here in this particular case as we increase the lag distance. So this is what we call the behavior at the origin. So the origin is 0. The behavior at the origin of the experimental correlogram is very different from this to that. So this behavior at the origin is something that will be another means of quantifying what we observe in these images. Okay, now what about noise? So again, I have an image whose correlation length is about 8, but also looks very different from the previous cases. And actually what we notice is that although our correlogram always starts at 1, we see a precipitative drop here in terms of that correlation length. And so this is due clearly to this image is much more noisy. It means that if I would go take a pixel and go from top to bottom, left to right, there's some kind of unpredictable element in there, which is simply a noisy component. And so this noisy component can have many origins, and we'll talk about that later when we talk about variogram modeling. First of all, there may just be a measurement of error. So if this would be a remote sensing image, let's say, you get this noise, or this is a geophysical image, this is noise, there's some noise to it simply because of the error in measurement. It could also be due to the fact that our discretization of our phenomena, or sampling distance between, say, the pixels that we have is too large in terms of discovering all the variability that is present. And so some of that variability that's not measured because it's smaller than the sampling space comes up as noise. So this is this Nyquist frequency idea we have also in signal analysis. So what's kind of nice is that you can also predict the amount of noise that we have simply by looking at the cutoff at the origin. So here we see that we have about 50% of our signal is noise and 50% of our signal is correlated. That means that, let's say 50% I cannot predict, and 50% I can have some idea of making that prediction because of the existence of spatial correlation. Okay, so now we get some more clear picture about this quantification. We have a number of issues or quantifications we discussed. There was the correlation length, which is what we can read off of the correlogram. Then we talked about smoothness, behavior at origin, which then that behavior at origin determines the amount of smoothness we see in the image. We discussed that correlation length may vary with direction, which is anisotropy. And then we discussed random noise. So in geostatistics, random noise will also be referred to as nugget. And I mentioned one source, which could simply be measurement error, but it doesn't have to be. We may perfectly measure everything and still have random noise. And here's some explanations of why this is. For example, here these are samples. So I measure, say, something. For example, let's say it's a gold nugget. Then you notice that we're missing some part of that gold nugget simply because, or that variability simply because the distance of my sample is too large. So there's something I'm missing in that variability that show up as nugget. Or my samples are too large, even if the distance is very small. You notice that I may miss some part of that variation, and that then shows up also as random noise. So that doesn't mean there is noise. Essentially, there is some systematic behavior that we're not capturing with our sampling. Okay, so the calculations we'll do in SGEMS, and I refer to the YouTube tutorials on SGEMS on how to do that. And so in SGEMS, you can load your data, and then there's a data analysis tab. You can calculate variogram, and then say what property would calculate the variogram of, and then there's a number of directions you will calculate the variogram, and then that shows up as something that looks like this, where we have correlograms for different directions. Okay, so now what with irregularly gridded data? So the problem with irregularly gridded data is that that idea of taking a particular vector and use it as a sliding window, a sliding vector over the grid is no longer possible. So because every distance between every point in this is unique. So the idea of gathering information about the same distance into a single scatter plot is no longer applied. So the solution to that is to give some tolerance to that. So we're not saying that everything has to be at exactly the same distance, but we'll allow for some tolerance in that definition. So what we'll do is we'll still slide now not over every single grid point. We'll slide over every single data point, and at every particular data point, we'll define sort of a tolerance cone, and that's what's shown here. So imagine that I'm calculating the variogram in the 45-degree direction. So if I calculate the variograph in the 45-degree direction, if I walk over this direction, I'll find no single data point that lies exactly along that direction. However, if I allow for some tolerance, then I notice that within that cone, there now I have a number of data points that lie along the 45-degree direction. So as you know, to calculate correlogram, I will need to not just define direction, but also lag distance. So again, we'll have to have some tolerance, because if I take exactly a lag distance, I notice that there's nothing there again. So I'll take some tolerance in terms of lag distance, and then I notice that there's some points that are within this class. You see maybe 2 points within that class and a number of points within that class. So now what I do is essentially I start moving this cone over all of the data points, and I start gathering information just as before. Now I just keep track of these distance classes and these directions, and I put the dots in the corresponding correlogram, and then I can calculate again a correlogram for a particular direction. If I want a different direction, then I need to move, of course, the angle here of that cone. So in many softwares, this is sort of it's implemented the same. You notice here it's just slightly different, but a similar concept. So there are basically 3 tolerances that we need to think about. The first is that of the lag distance. So that's the size of this piece of the pie here, let's say. Then we have the angle tolerance, is that how far our pie or our pizza is. And then also at some point, you'll notice that that points, this cone will just keep on continuing, and so points that are far apart will get amalgamated into into the same direction, even though they don't lie around that direction. So I need to also calculate some kind of a tolerance, a bandwidth that a maximum bandwidth that I will allow around that. So this would be that bandwidth. So there's a number of things to note here, which is the angle tolerance, lag tolerance, and the bandwidth. So if I do that, you say, well, where did these things come from? Well, that requires a little bit of tuning. We'll talk about that in the YouTube lecture. And so then I can calculate the correlograms here. And then we notice again that we notice correlation lengths. We see some where it appears to be a noise, and we see it appears to be not really much variation with angle distance. So it's probably isotropic. Now, of course, these correlograms don't look as nice as before, simply because I have much less data to calculate them. And so the sampling variation is going to come into play when you calculate correlation coefficients. Here we see a bit of a more complex example, namely a porphyry copper deposit. So on the left-hand side, we have the copper grades. On the right-hand side, we have some idea of the nature of lithology. So, of course, in this porphyry copper deposit, where the mineralization comes from the bottom up, we see quite a lot of continuity into vertical direction and less so, more variability in the horizontal direction. So this is somewhat different from, say, aquifer systems or red rose systems, where we expect, because of the layering of the system, more continuity in the horizontal than in the vertical. Again, in SGEMS, which I'll discuss in the YouTube videos on SGEMS, we get the same kind of things here, which is you have to specify tolerances, specify number of directions, and so SGEMS gives you some guide on how to do that. So once we do that, and we can calculate along various directions, then we get here a correlogram along various directions. And so what you notice immediately is that we have a nugget effect, clearly about 50, say 60%. And also, if you look at the, let's find it here. Yep, here is the, no, this is azimuth depth here is 90. So that means this is the vertical variogram. And we notice that we have indeed a correlation length, say around 20, while in the others we have a much smaller correlation length, 15.5. So the units here are simply the units of the model. Which this area is about 60 by 60 by 50. So, so these are not necessarily real coordinates. Okay, let's have another look at the same scatterplot. So as we've done before, we make the scatterplot, which is cross-plotting, scatterplotting essentially a value at location X versus a value at location X and a constant lag distance. So previously we calculated the correlation coefficient. What we'll do now is essentially we calculate the distance of any of these crosses away from that 45-degree line. If you look into that, then you'll find that there's half the square difference between those two values. So what I do now is I'll sum up all those distances and average them, and what I get is this equation here. So this is called the experimental variogram. Essentially, it's what is called the semi-variogram, which has to do with that half here. So if you move that half, you get the variogram, otherwise the semi-variogram. So in most of the lectures, and this is also what most people do, is we sort of don't bother saying semi, we just say variogram, and then we sort of find the right context. Within the right context, we know what we're talking about. So now instead of calculating a correlation coefficient, I calculate a square difference. And so there's some differences that we have to note, and we'll talk about that in a bit about with the correlogram and the variogram. So what is the relationship between all these functions? Well, this is sort of a summary of that. Basically, what you have is you have an R correlation function, starts at 1, goes down. Then we also what is known the covariance function. So we know that the relationship between a correlation coefficient and a covariance is simply the standardization by variance. So if I multiply with variance, I get the covariance function. So the shape of that function doesn't change, obviously, if you multiply with a constant. And then I flip the function around. So I subtract basically the variance and take the negative of that, and I find here the variogram. So again, the shape of that function is not going to change much or at all. The only thing that's different now, of course, is that we start at 0, we start to increase this function, and then at some point it levels off, just like it leveled off over here, but it levels off at the variance of C. It doesn't level off at 0 anymore. So the variogram is essentially a measure of dissimilarity, in the sense that the further we go along this distance, the higher the variogram value becomes. So it measures dissimilarity. So compared to correlogram, where the higher we go along this axis, the smaller that value becomes. So that's a measure of similarity. So essentially, they measure the same phenomenon, but in different ways. So if you apply that to the copper case, then as you notice, these functions now get flipped over, and so we get essentially the same result, namely where in the dip direction we have a larger continuity than in the other direction. So you say, why use variograms, geostatistics, and not covariance? If you look at the equation of variogram versus covariance or correlogram, so the correlogram would just simply be standardized by variance here. We notice a difference, which is in this equation, I don't have the mean, and in this equation, I do. So the variogram estimates do not require knowledge of the mean. And that's an important part. It theoretically has some interesting importance in terms of the stationary assumptions that we're going to have to make to do estimation. But practically, it also has some really important influences. And it is, of course, that the mean may not exist. We saw that in the first session of this course, is that you may have very skewed distributions for which the mean doesn't exist. And secondly, if you're estimating a covariance that's based on another estimate that's unknown, then you may end up having bias. And so this bias has been reported, and so is an issue in terms of the covariance that you don't have with the variogram. So the nomenclature also changes a little bit as compared to the correlogram. That has just to do with the geostatistical jargon and literature and heritage. So we no longer talk about random noise, but we talk about nugget. We saw that discussion before. We no longer talk about variance, but we talk about SIL, and we no longer talk about correlation length, but we talk about range. But these are just naming things. The fundamental issues, of course, do not change. So there are many things you can discover in variograms, not just SIL and a range, a nugget effect, but also, for example, cyclicity. So, for example, here we have a sort of a cross-bedding sandstone, and imagine we have here measured porosity. Let's say, then it's clear that if I look in the vertical direction, that I see this repetition of these bedding, and so this repetition shows up as cycles in the variogram. It essentially means that yes, the variogram increases. It means the dissimilarity increases, but at some point when you go into a cycle, then again you get correlation, which has to do with the fact that these beds here correlate, this here correlates well with this, and so that would lead to that drop in correlation, and that's what we then see, and that may then, of course, having many periods. So this is clearly that cyclicity shows up into sort of this wobbling of the variogram function. Now, you shouldn't over-interpret, this has to be very clear. Many variograms wobble just because they are noisy. So if you get this very clear sort of sinuous function, then that will be an indication of cyclicity. About trends. So here we have actually a log where we measure porosity. We notice here in this particular case, porosity is increasing with depth. So that shows up in the variogram essentially in the fact that there's no apparent SIL. So it doesn't sort of level off around the variance here, but it just keeps on increasing. And that sort of makes sense, obviously. That is, namely, that if I increase the lag distance, then I see increasing dissimilarity in values that have to do with the trend, not necessarily with just random variation around that trend. So if I remove that trend, then I would see a variogram that would have that still. And that's something, of course, that we'll have to talk about when we talk about estimation, because we'll have to estimate this residual component, and the mean component will be treated in a more deterministic fashion. So there may be systematic trend. This is another example where you have systematic trend. So you clearly see if we can go from top to bottom, we see some kind of a linear increase in value. And so if you calculate the variogram of that left picture, then we see indeed that you get this nice increase in that variogram. So even that linear increase in that variogram leads to this increase in that, a linear increase in the property leads to some kind of a nonlinear increase in the variogram. So if we remove the trend, in that particular case, is simply removing some kind of a constant xy plane, then we get this residual variogram. So you notice that this looks now very different from this picture here. So trends can be complex, don't have to be simple. For example, I have this data, I do some biharmonic spline interpolation, I get this quite complicated trend model, remove that from the data, just subtract the data with whatever I find in this picture, and we get now a residual variogram. And see, still we have correlation left. That means that the biharmonic spline doesn't necessarily explain all the variation that's in the data. And that's why later on in the course we'll talk about kriging. Kriging is a more sophisticated technique essentially than spline interpolation, in the sense that it accounts for both of these types of variation. Okay, we'll have to talk also about various types of anisotropy. So we talked about one form of anisotropy before, which is called geometric anisotropy. So in geometric anisotropy, it's essentially what we have in this picture here. In geometric anisotropy, we are talking about variation of the range, or correlation length, as function of direction. And so clearly in this bottom picture, we see that we have more variation in east-west direction. So we have less variation in the east-west direction and more variation in the vertical direction. So here we essentially get something even more sophisticated. You notice if you look at this picture versus that picture, then here we see that the stratification is even stronger. The difference between this picture and that picture is as follows. So imagine you start here at this red area, and you would walk along a horizontal. What you would notice here in this picture is that you basically stay mostly in the red and the greens. For example, here you stay in the red and the greens. You don't go into the blues. This is different here. If I start at some value, let's say over here, red, then I can actually go and get more variation along the horizontal. So what that means is that that the variation in terms of variance, right? Because if I go up and down, basically from red to green to red, basically that's a variance. If I calculate the variance in that direction, I will find that the variance here in this direction is smaller than the variance in that direction. So there's a second kind of type of anisotropy, which is called zonal anisotropy, where we see a change in variance into the variogram. So that is manifesting here, namely here, and this is our kind of original idea of the idea of geometric anisotropy, where you notice that if I take the vertical versus east-west, I get a change in variance, and change in range, correlation length, which is pretty clear here. It's 30 versus say 5. But when I look at this top picture, I also notice on top of that a change in a drop into the east-west direction of variance. So the variance is only a half here of what it used to be in this picture. So that is called zonal anisotropy. And so on the previous slide, then you can start mixing various issues. For example, here you have only zonal, here you have different kind of geometric with zonal, etc. You can make different kind of combinations of zonal and geometric anisotropy. So what if you're dealing with variables that don't have necessarily an ordinal value? So for example, if I have 3 lithologies, such as shown in this particular sedimentary system. So in that case, we can't just call them 1, 2, 3 because that will influence our results in terms of the ordering of these lithologies. With different ordering, we'd get different results. So the way around that is to create what's called an indicator variable. An indicator variable is simply saying it's transforming these 3 categories into these 3 indicator variables, which, for example, iRed would be the first, would be one indicator variable. That is saying basically what I do is I say I keep the red as 1 and the rest I call blue. So basically what that means is that I take the green and make it blue, and then I have basically 2 categories. And then I calculate the variogram would be the variogram of this red category. So you notice that I can repeat that for each category. And so, for example, if you do that for the green category, then you get this variogram here. And so we notice, yes, for the red category, we see if you go in the vertical, these are the vertical variograms. We notice that we have a short correlation length, which has to do with the fact that this red is much more thin featured than the green. And also, if you look at the green, we notice that we have more green on top than in the bottom. So we get this trend essentially in the green. Okay, so in the SGEMS YouTube session, we'll talk a lot about good rules and suggestions about calculating variograms and how to interpret them. And so we'll revisit these particular suggestions then.